In this lab, we are told that a star is orbiting a black hole of unknown mass. In analyzing the star's motion, we already used the position data and time step given to us, assuming the gravitational pull between the two objects is the only force, to find the mass of the black hole. The goal of this lab is for students to use their knowledge of gravitational forces and the parallel and perpendicular coordinate system to estimate the mass of the black hole. To find the mass of the black hole, we know we have to use Newton's law of universal gravitation, the idea that all massive objects in the universe attract all other massive objects in the universe, with the equation force of gravity equals the universal constant g times the masses of the two objects over the distance between them squared. Using this equation, we can solve for the unknown we are looking for, the mass of the black hole, which then becomes the force of gravity times the distance squared over g times the mass of the first object, the star. The location of the black hole is given to us as 4e10, negative 1e10, 0 meters, and because the star is orbiting the black hole, its position constantly changes. The changing locations of the star are provided to us in a CSV file, which allows us to illustrate the star moving around the black hole in the computational model. The problem gives us the mass of the star as 1.9890 e to the 30th kilograms, and we know that g is a universal constant. What we need is to find the force of gravity, which we know to be the net force because it is the only force acting on these objects. From here, we can use the momentum principle for our time step of 1 day, or 86,400 seconds. The change of momentum over the change in time would equal the net force. Then, using what we know about dp dt, that the net force is equal to the sum of the perpendicular and parallel components, we can define these and find our net force, which we did in the code. You can see three different arrows moving with the star's path. There's a blue one that points toward the black hole at the origin at all times, illustrating the perpendicular component of the momentum as it points toward the center of the kissing circle. The black arrow that points in the direction of the star's motion follows the parallel component of the net force. It switches directions depending on where the star is located in relation to the black hole. As the star approaches and becomes closer to the black hole, the gravitational force becomes stronger and causes the parallel component to share the same direction as the star's motion. But as the star gets further away, the force decreases and the star slows down, causing the parallel arrow to flip and point in the opposite direction of the star's motion. And then there's the yellow arrow, which shows the net force on the star, the sum of the black and the blue arrows. And then the question asks the differences between the net force and dp dt. We know that the net force is equal to dp dt. We also know that the net force of the parallel component is equal to the parallel component of dp dt. Same for the perpendicular component. What's different between these two is how we would go about solving them. To solve for the net force in this case, you would use the universal constant g times the mass of the first object times the mass of the second object over the distance between them squared. But in general, the net force would be the sum of all the existing forces. The dp dt would be found using the mass and velocity of the object in motion, because dp dt equals the mass times dv dt, or by finding the parallel and perpendicular forces and adding them all, you can get the total net dp dt. If the black hole whose mass you found was removed, and a different black hole was placed in the same location, you would not find a different mass. The values used to calculate the mass of this black hole would be the same, so we would get the same answer.